what are we going to be doing today? Very simple, right? So aerodynamic simulation needs, why do we need them? What is it that engineers and reputed companies are trying to understand and optimize? We'll all try and understand that. And then we'll talk about some background work, like, how this has been done, how this has been done 20 years ago, how things are moving towards in the current day. We'll talk about design methodology. Here, we will primarily focus on how computational fluid dynamics is being used in the design process. Then one thing that we typically don't do is a practical session. For example, yesterday we had a similar session on internal combustion engine simulation, where the focus was on IC engine simulation. There, I did show the IC engine model, but I really did not talk about how it was set up a lot. So today I'm going to be, providing a little bit more information on how a commercial software can be used to set up an aerodynamic simulation in a very similar manner to, say, how an engineer in General Electric or General Motors would do. Apologies for that. Put my mobile in silent. And then obviously we'll be doing some post-processing, and this time it's going to be interactive post-processing. And I'll show you what are some of the results that engineers look at, especially while designing, say, F1 cars, right? Since I did notice that two of them are interested in external aerodynamics, I thought I would talk about that. Okay, so we'll start with a very simple, clean slide, right? So aerodynamic simulations, why do we need them? Why do we need aerodynamic simulations? Can anyone answer this question? To better understand airflow around the vehicle. Akhilesh, all right. Thank you for your response, Akhilesh. How about others? Does anyone have a different viewpoint? To study the flow behavior, okay. For predicting drag and lift coefficient of a vehicle. Deepak, all right. To study about drag and flow parameters, Shivananda, all right. Bhavana Chandra Reddy, dynamics of flow can be understood, okay. To know response of fluid flow involved with various things to find out how the vehicle responds. All right, so you can kind of see that all of the answers basically can be grouped into a single answer, right? So when you're trying to simulate, you can determine how the fluid flow is, right? That is what all of you guys are saying. But the important question that you need to understand is, well, but why is CFD used for that? Why can't you directly visualize the fluid flow? Isn't that more accurate? Why do we need to simulate them, right? That is the important question that you need to ask. So for example, this right here is what you call as a NASA generic conventional model truck. So let me just put some arrows here. Just give me a second. So for example, this right here, Kenil Patel, I'm an aerodynamist in the Formula Electric team at VIT University. Okay, that's pretty cool, Kenil. Welcome to the workshop. Okay, so this right here is a GCM truck. So GCM stands for Generic Conventional Model Truck, right? So this is basically a CAD model, right? So we have a CAD model here, and I'll be showing you more pictures later. Now, the reason why people do analysis on this is because a lot of experimental data is available. So people have actually measured the things that you guys are talking about, like drag coefficient, and then any lateral movements, which you can basically measure by putting a yaw on the truck, right? And they have also measured more data in terms of transient pressure, meaning when fluid is flowing over an object, right, it exerts a particular pressure, correct? And from this pressure, you can calculate your drag force. But this pressure is changing as a function of time. So that is what you call as a transient data. So transient means something that is changing with time. So people have already done experiments where they are able to capture time accurate data of pressure, velocity on top of the truck, right? So which means I can actually calculate what the drag coefficient is, right? Very, very accurately. So now let's talk about the same question again. So if I can accurately measure my drag coefficient through experiments, then why do we need aerodynamic simulations? Would that be more accurate than the real life experiments? Most likely not. But why do we need these simulations? Can anyone answer that question? Exactly. So whatever Ashish is saying is the right answer. So why do we need aerodynamic simulations? Well, it is not because it's more predictive. It's not because it can actually give you things that experiments cannot. It's primarily a very cost-effective tool. It does not help you in better understanding of flow patterns. It does provide you a visual aid, but you can never be sure that your CFD simulation is 100% accurate. The primary purpose is, you see, for example, if you want to reduce drag coefficient and you have a concept, right? Say that you have a concept, meaning, okay, if I basically reduce my flow separation point, I can reduce the drag coefficient. You have this theoretical knowledge that you learned from fluid mechanics. You're going to apply that by maybe using a spoiler, or you're basically adding this vortex generator on top of the truck so that separation point is going to be delayed. You can test these strategies quite easily if you just have a good computer, right? And you don't need a wind tunnel, right? Or else you need a wind tunnel to do the entire process. So the reason why you need CFD is it's a cost-effective tool at the end of the day. If you're building a wind tunnel, each and every test is going to cost around $20,000 to $30,000. This is just a single point. Typically, when you run aerodynamic simulations, you run 50 to 60 iterations per design change. Again, I'm talking about industry standard here. I'm not talking about something that you would do for, say, your FSA teams or Supra teams, right? And you need larger computers also, right? So bottom line, aerodynamic simulation is a cheaper tool and it will help you reduce your testing time. That's it. But what you need to be careful is, for the exact same reason, many people think that it is very easy to do aerodynamic simulations, and they try to do it and they assume that what results they are getting is very, very correct. Especially, I'm not sure how many of you are in FSAE or Baha teams. For example, Kenil Patel, I think, is in the Aero team. So how many of you who are in external Aero teams or who have done external Aero simulations, you guys have run simulations using a desktop computer? For example, Kenil Patel, have you run any type of CFD simulation, like underbody aerodynamics, for example? Okay, so Deepak, then you should also be able to answer. So Deepak, like, what type of computing platform did you use? And Rushikesh, what type of computing platform did you use? Meaning, did you run the simulations on a laptop, or how did you run it? Or was it a desktop computer? I'm not asking about the software, I'm asking about the computing platform. Like what type of hardware resources did you use? Was it like your laptop computer, like 4 to 8 GB of RAM? Rushikesh, college computer, 16 GB of RAM, all right. Deepak, how about you? And Kenil Patel, how about you? Again, guys, sharing this information will help others understand as well. Deepak, 16 GB of RAM, all right. Okay, I think that's good enough data set, right? So not to pick on you guys, right? But 95%, I can say this with 95% of confidence that your simulations are wrong. Why? Just by looking at the computer configuration, I can say that your external aerodynamic simulations are most likely incorrect, meaning you will still get the results, but the drag coefficient that you think that you're getting is most likely off. It can be quite off. I'm talking about an error percentage of 25 or more, right? If you have 25% error on something, then that's as good as completely wrong, right? So why does this happen, right? I mean, and from your viewpoint, Rushikesh and Deepak, you guys might be thinking that, well, I'm actually using ANSYS. How can I get wrong answers? What about drag curves? Well, if you're talking about drag coefficient, that should be even more wrong. Getting the lift is typically easy. For example, getting the downforce is easy, but getting the drag coefficient is much harder. And I'll explain the actual analytical reasons for my statements. Like, why am I saying that your simulation's wrong? I'll be explaining that, right? Now, in case of a truck, you're looking at, for example, what the drag coefficient is. And you basically position the truck at different yaw angles, meaning a truck is not always going to go straight, meaning the airflow that the truck experiences is not going to approach it straight up to its face. Sometimes there is lateral forces, right? So you take a truck and you rotate it by 10-15 degrees, which is what you call as yaw, and then you perform the same simulations, right? And the reason why you're doing this is you kind of understand the overall design and the effect that this design has on its aerodynamic performance. You have to look at the entire picture. But sometimes the objective is different. For example, this, as most of you will recognize, is the front wing of a F1 car, right? And one of the things that has been very well designed and is found in pretty much every F1 car is the end plate. Does anyone know what the end plate is for? And especially the F1 enthusiast. Can you guys tell me what's the use of the end plate and what is the use of this turning vanes? Ashish Kumar, what about the internal flow hardware? Internal flow hardware. Ashish, you need to rephrase your question, meaning give me more context. Your question is not clear to me. Exactly. So Akhilesh, you guys are right. But for those of you who are not huge fans of F1 cars, these end plates and vanes are used to actually divert your airflow away from the wheels. If you can just imagine a little bit, and let me try to draw in 3D here, which I don't do very well, but you can imagine that your tires are going to be somewhere here, right? So these vanes are basically used to divert air around the tires. Well, why? The reason is quite simple. Any rotating object is going to have bad aerodynamic performance, right? It's going to disrupt the flow, which means it's bad for aerodynamics. The whole idea behind aerodynamics is, especially for racing applications, is your car should be smooth enough that it has very, very minimal resistance to the air. It has to cut through the air quite easily. And when there is a rotating object and when there is air coming right up front, it's very bad. It's going to cause a lot of drag force. In other words, there's going to be a lot of pressure loss. You're trying to minimize the pressure loss by smoothly navigating the airflow, and end plates are just a technology for that. The other purpose for doing this is when you're reducing the airflow to the front tires, they're not cooled very well. Okay, and one of the things that you might or might not know is, with respect to a F1 car, the braking performance improves as the temperature of the tire increases, correct? Some of you might have heard of this. And since you're not cooling the front wheels, you're actually helping it increase its temperature quite well, which means your braking performance is going to hit its maximum value quite sooner, which is good, right? Because these people drive at ridiculous speeds and they need their brakes to work as effective as possible. The third functionality that the wing provides, out of many functionalities, is providing downforce. So one thing you need to understand is that for a car, for a F1 car, especially for racing applications, it's designed for downforce. What does downforce mean? Well, when your car is traveling at high speeds, the pressure acts on the wings in such a way that there's a large amount of downward force which keeps your car and it helps you stick to the ground. Exactly. Negative lift, sure. But basically it's a force component acting towards the ground. How does this help? Well, if you're turning in sharp corners or turning in corners at a very high speed, it helps you keep grounded, right? So based upon whatever you're trying to achieve, your objectives will change. But remember, the reason why you're still trying to do aerodynamic simulations is not because CFD will give you the results accurately. As I will talk about in a later slide, the very term computational fluid dynamics means you're approximating your solution. So you will have some errors. The only reason simulation is being used, again, I cannot repeat myself enough, is it's a very cheap tool, right? You can actually run several iterations. For example, in this case, I can try out different end plate designs, And I can run a lot of simulations and figure out, okay, this end plate is much better than the other end plate. Not in terms of absolute values, but in terms of trend. And that is where CFD shines. So for example, say that you have 5 front wing designs and you take them to the wind tunnel and you basically see which front wing is the best, right? You can get a number for it in terms of say downforce. When you're running CFD simulations on exactly the same set of 5 front wings, it's the chance of you getting the downforce exactly, like with 1% error, the chances of that happening are very low. But the chances of predicting which front wing is better is quite high. And that is why I'm saying that CFD is good for predicting trends and not so much for predicting absolute values. So the guys who are doing CFD simulations, in your case, the error is probably more because you're not throwing enough computing power at these type of simulations. But if you do say that you are able to get a machine that has 64 GB of RAM, then you can maybe run a decent simulation. That's the minimum computing power that you need. And if you have a computer like that, then you can expect that, okay, if I have 2 designs, then design B seems to be better in the simulation. Well, that means in real life, that's going to be better. You can have that confidence. And like I said, the absolute way to evaluate aerodynamic performance is your wind tunnel. So what is wind tunnel? It's basically a large room, right? And there is a stream of air flowing at constant velocity, and the velocity of the air can be controlled very precisely. And you have your object, right? So this right here is your GCM truck. Okay, so this right here is your GCM truck. And what we are doing is we are just letting the air flow through the truck. And you can see that there are a lot of points here. So if I use a different color, maybe black, you can see that there are so many points. So these are what you call as pressure tabs. In other words, these are nothing but pressure sensors. They will basically record the pressure at that point at a given point in time. So they are really precise. And you have you have around 200 pressure sensors on the entire truck surface. So the advantage is once you have this pressure data, you basically have a pressure distribution, which basically says in which area you are having low pressure, right? So remember, usually in the front of the truck, you have high pressure, and usually in the back of the truck, you have low pressure. This difference in pressure is what is actually stopping the truck. That is the air resistance, correct? So the whole idea is to identify these low pressure areas and see if there is something that you can do to basically minimize the pressure loss. That is, at the end of the day, the job of an aerodynamics engineer in any company. It's easier said than being done, but that's the whole job of an aerodynamics engineer. Forget the full form of GCM. G stands for generic, C stands for conventional, M stands for model. Now, when you look at this truck, like, can anyone tell me what is weird about this truck? Does this truck look normal to you guys? What is weird about this truck? Can anyone answer this question? Just look at the truck and tell me if you find something weird about it. Ashish, I would appreciate it if you first ask questions with respect to what is being shown on the slide. I'll definitely answer your question towards the end. It's a scaled prototype. Well, this being a scaled prototype is fine, right, Ashish? But I'm asking this, there's something weird about this truck. What is that? Can anyone see it? Okay, I'll give a clue. It's right here. The front design, all right. It's placed at an angle. No, that's not a problem. That's what you call as a yaw, Rishikesh. This is what you call as a yaw. If you place it exactly, along the axis of the wind tunnel, then that is going to be a zero yaw case. Akhilesh, the design is not optimal. Well, guys, these are all minor things. Whatever you're saying is minor things. Let me ask a simple question. Does this look like a real truck or does it look like a toy truck? It'll model Shazad, maybe try to give a longer answer. It looks like a toy truck, right? Exactly. So why put a toy truck in a wind tunnel? What do you guys think? Why would someone do this? And why would someone put 200 or 300 pressure sensors? And these pressure sensors, just to go into a little bit more detail, so these are transient high frequency pressure sensors. They can basically measure pressure at a very high frequency, meaning you have excellent time resolution. So these pressure sensors are usually very costly. And this particular truck has around 200 of those pressure sensors. Why would you do it? It is scaled down to reduce cost. Well, if you have to reduce cost, I don't think cost is the issue, right? You're spending so much on pressure sensors alone. The cost of the truck is not a big deal. For testing big truck, we need huge wind tunnel. Yes, that's correct, but I'm saying the wind tunnel is just a one-time expense, right? And this is basically NASA's. This is a model that NASA built, so money is not an issue. Again, think of it like engineers, right? And these are the things that you guys need to understand. Like why, when people show you wind tunnel simulations, it's cool and stuff. It's cool, that's correct. But why would they do that in the first place? More pressure sensors will require for bigger trucks? Not really. It's basically surface area coverage, right? That's not a big deal. It's a metal model. Okay, so Shivananda, so what? Well, okay. Let me just give a little bit more hint, or actually I'll give the answer right away. So the GCM initiative was done primarily for validating computational codes. And this slide basically helps you understand why CFD is a great option for aerodynamists. So when you run wind tunnel tests, right, these are very, very expensive, as many of you pointed out, right? And there are softwares like ANSYS Fluent, Star CCM, Converge CFD. There are so many softwares. Yeah, and obviously they give good results. But the problem is, how do you know if you're getting good results? For example, the guys who actually did external flow analysis, Deepak Kumar, and I forgot the other person's name, Kenil Patel, yes. How do you guys know that the drag coefficient that you're getting is correct? Is there a way for you guys to know it? How can you trust the number that the computer is giving you? The short answer is you can't. Unless you have done the same problem before and you have done experiments on it, you can never be sure that your answers are right. Exactly, right? So you need to validate, and that is exactly why the GCM was built in a simpler way. So the objective behind the GCM program was to actually create very high quality experimental data on a model that is very simple to mesh and run CFD analysis on. So the reason why the model is so simplified is you can take this model into any CAD program or any meshing program, and the mesh generation process is going to be super easy. One thing that you don't see in this truck is that it basically does not have any underbody, right? Again, I cannot show you that. This is just a picture, but you have to kind of believe me. If I actually rotate the truck, maybe let me see if I have a picture. Actually, I don't. So basically, if you rotate the truck, you will see that there is no underbody. Why? Usually, if you have an underbody, that means you will need to use advanced cleanup tools to clean the model. And when you do that, you slightly deform the truck, right? And that because of that, your CFD results are going to change. So what people do is, what people did at NASA is they made the model so simple that pretty much any CFD solver out there would create almost an identical mesh. So if the mesh is identical, all the results boil down to what governing equations you're solving, what is the algorithm that you're using to solve, what type of turbulence modeling schemes you use, right? So you can basically do a validation study, and that is the first thing that everyone needs to do. You need to validate your CFD code, and then based upon the validation, you can figure out that, okay, if I'm able to validate an external flow problem at this Reynolds number, then for that same Reynolds number, if I modify the geometry, most likely I'm going to get the accurate answer, or most likely I'm going to get a very close answer. That is why this is being done. So for all of those F1 enthusiasts and CFD enthusiasts in the group, this GCM data is public. You can download it, and you can actually, the model is also available. I'm not sure in which link it is, but it is. You can actually download the model, and you can actually run run numerical studies on it using the hardware that you have, and compare the results that you're getting with the experimental data. And that way you will establish more confidence in your CFD methodology. Any questions regarding this slide? Any questions or comments? If you guys don't have any questions, then you can just say no. That way I'll just move on. No questions, Shehzad. Okay, perfect. How about others? No questions, Rishikesh. Okay, cool. So drawbacks of traditional testing. Deepak Kumar, what is the best way to find that these simulations are right? So like I said, that is basically, the process of validation, Deepak Kumar. So what you ideally need to do is, since you are interested in aerodynamics, you should basically download the data set for the GCM Truck. And if you're using ANSYS or any other modeling CFD software, you have to run the same simulation with ANSYS, and you need to use the right computational mesh. Okay, and you need to calculate drag coefficient. And the nice thing about the GCM Truck is they have drag coefficient for several conditions, maybe around 20 to 30 conditions, right? Just take 5-6 conditions, and for those 5-6 conditions, run your computer simulations. And Shivananda, I'm kind of answering your question as well. So take 5 to 6 experimental configurations, and for those configurations, run your CFD simulation. If their answers are deviating, well, what is the error? If it is within 5%, it's okay. And then what you need to do is you need to see if you're getting the same trend as your experimental data. If you are, then you can actually use the same mesh strategy, the solution algorithm strategy, and apply it for your case. So Shivananda, does that answer your question? Shivananda and Deepak? What shall be the number of iteration? That's a great question. Well, that depends upon the problem that you're solving. Ideally, you should not be looking at the iteration. You should be looking at convergence, meaning, say you're looking at drag coefficient, right? The drag coefficient is going to be changing with respect to each iteration. But if the simulation runs long enough, the drag coefficient is going to start fluctuating about a mean value. So let me just explain that. So what's going to happen is, say that this is actually iteration, and you're looking at drag coefficient. So your drag coefficient initially can be 0 when the simulation starts, but then after some time, it's going to go up and then start doing this. You need to wait till this happens. And then at this point, you can actually take an average. And this average value is going to be your CD. Average CD should vary very less, exactly. And then this is basically your baseline. So this can be for a particular angle of attack. So alpha can be 0, where alpha is the angle of attack. And you basically do the same thing for different angles, right? And you will basically get a trend. So for example, if you're looking at lift coefficient, you will have something like this, right? And similarly, if you have drag coefficient, your drag is going to keep on increasing as your angle of attack increases, right? And this is basically your stall point or the choke point where flow separation is bad. And you need to make sure that if this red line is your experimental data, then you need to basically perform experiments and say you need to perform simulations, and your simulations, for some reason the color did not change. So let me use symbols. So your simulation should kind of be at least something like this. There should be at least the trend. There will definitely be an error. Okay, so you need to get to this point, and this requires a lot of time and patience. So Deepak, does that make sense? Shivananda, what should be the range of error? Well, see, that depends on the quantity. Usually for drag coefficients, you should be able to, if you're using the right turbulence model and the computational mesh, you should be able to get it within 5%. Especially in the no stall area. So in this area, so this is basically a stall region when the flow separates. Before the flow separation, your error should definitely be less than 5%, for sure. If it is not, then most likely you're setting up things incorrectly. Those are great questions, Shahzad and others. Great questions, guys. Keep them coming. Okay. Any other questions? Does anyone else have any other questions that I can answer? Okay, looks like there are no questions. All right, so let me move on to the next slide. Computational testing, right? So far we have looked at traditional testing, which is all about wind tunnel. So now computational testing is all about solving some equations. So CFD. F stands for fluid, D stands for dynamics. So CFD stands for computational fluid dynamics. Okay, what does CFD mean? Well, CFD basically is the art of simulating fluid flow using a computer. So for example, say that this is a cylinder, you're simulating flow, right? And you're using a computer to do it. So that's a laptop, right? So the technique of doing this is called as computational fluid dynamics. How does this work? How does it actually work? Well, it all starts with what you call as the governing equations. So what are the governing equations? So the governing equations are nothing but mathematical formulas that represent your fundamental laws. So what are some of the first principles that you have studied? Especially if you have taken a course on thermodynamics or fluid mechanics, you know this. What are some of the conservation laws or first principles that you have studied? Can anyone answer that question? Exactly, mass, energy conservation, momentum conservation. Great. Okay, so looks like there was a question. Deepak, what does the stall point indicate? So stall point indicates that the flow is separating, right? Meaning your boundary layer is detached, and that is going to cause a huge wake region. That's going to be a source of low pressure, which is going to increase your drag coefficient tremendously. Exactly. So as far as the governing equations are concerned, mass, momentum, energy, these are all conserved quantities, meaning they can neither be created nor be destroyed, but they're conserved. Meaning, say that you have a box, right? Say that you have a box. Oops, sorry. Say that you have a box like this. And then in this box, I'm going to have mass that's coming in at 1 kg per second, right? And there's going to be mass that's going to be leaving at the rate of 0.5 kg per second. So what's going to happen to the mass inside the tank? Can anyone answer? Exactly, right? So it increases at the rate of 0.5 kg per second. So, when you put it in numbers, that's very easy, right? So this is nothing but dm by dt, right? The unit of m is kg, t is seconds. So dm by dt is nothing but, well, depending on how you define it, it's going to be q in minus q out in this case, right? So this right here is a conservation law. All right. Now the thing is, this is going to be just, you're looking at one dimensions, right? So flow is coming in here and going out here. Now say that you're considering 3 dimensions. Well, you need to basically do the same balance in 6 spaces, correct? When you do that, you basically get what you call as the continuity equation. Similarly, when you take this control volume, the 6-phased control volume, and if you balance force, then that's where you get momentum equation. Now remember, force is a vector quantity. It has 3 components. So this is Fx, Fy, and Fz, right? And these are your governing equations. These are partial differential equations, which basically say, hey, these are the rules that your fluid should never disobey. And finally, you have your energy equation, which is a scalar equation. Now, what is CFD? If someone asks you, it is basically solving these partial differential equations using a computer. That's it. If you're doing that, that means you're doing CFD. Now, okay, we have definitely made some progress, but what does that mean? How do I take these partial differential equations and solve it? Well, for that, you need to understand a little bit more about these PDEs. So first question, what is the order of this PDE? Can anyone answer? Shahzad, it's Shahzad saying 2. How about others? what do others think? Is it a second order PDE? Is it a first order PDE, or is it a third order PDE? If you don't know, you can just say don't know. That's fine as well. Deepak Kumar 3, Bhavana 2. Any more answers? Akhilesh 3. Anyone else wants to try? Taruna 2. Okay. So I think many people are saying 2, some people are saying 3. The answer is second order, okay? But can anyone tell me where the second order term is included? Where can I find the second order term? Because see, a second order term is going to look something like dou square u by dou x square. That is a second order term, but I don't see any term like that here. Exactly, it's the viscosity term. So for example, if you take Shazad, what do you do currently? Are you a MTech student or are you a BTech student? So if you take these terms, your shear stress is nothing but, you would have studied an expression like this, right? Tau equals mu times the strain rate, or dou u by dou y. So if you take, okay, got it, makes sense. So if you take this expression, which you have studied in undergrad, and you take another derivative of that, right? Since it's tau xx, you'll basically get dou by dou x of, dou u by dou x. So that's going to lead to dou square u by dou x square. So these are called as the viscosity terms. They are also called as diffusion terms, right? Because they help in diffusing the momentum, correct? So what we are basically saying is in this partial differential equation, we are saying that, okay, so if there is a fluid molecule and if the fluid is being pushed by other fluids, how does the force balance, right? That is what you're trying to represent here. So there are several types of sources that contribute to the forces that are acting on a control volume. The first thing is convective acceleration, meaning when a fluid molecule basically hits the other molecule, there is some amount of momentum transfer, right? That is being captured by these terms. These are the non-linear terms, and these are called as convective accelerations. And then obviously, if you have a pressure drop, meaning if there's a difference in static pressure, then there's going to be flow, right? There's going to be momentum transfer. That is dou p by dou x, which is called as the pressure gradient term. Similarly, if you have momentum, the momentum can also diffuse because of shear stress, meaning a particular layer of fluid can influence the neighboring layer of fluid. That is called a shear stress, and these terms are called as shear stress terms or viscosity terms or diffusion terms. Now, each and every term carries important physics, and when you're solving these terms, right, these terms are what give your engineering results. For example, when you solve for shear stress, you're able to calculate your drag coefficient correctly, right? Similarly, if you want to calculate the effect of pressure loss, or if you want to calculate pressure drop accurately, then you need to have the dpdx term, right? Similarly, if you want to get your velocity components correct, you pretty much need all the terms. So let me ask you a simple question. Say that you are running an aerodynamic simulation and you want to calculate the drag coefficient. Which term is the most important term? Like which term should definitely be there in the equation? Can anyone answer this question? I'll just repeat. If I'm doing external airflow simulation, which term should definitely be there in the equation? In other words, like if it's okay to remove certain terms, which term should never be removed? Viscosity. That was actually a trick question. The answer is you cannot remove any of these terms because this is a coupled system, right? Why is it called a coupled system? Well, if you take a look at your shear stress, that shear stress basically depends on your velocity, right? And your velocity depends on your pressure. Your x component of velocity depends on the other components, and everything is coupled, meaning the only way you can ignore a term is if the effect of the term is small. But if you have to calculate drag coefficient accurately, you cannot ignore any of these terms. So all the terms are important. Just remember that. The reason why people still simplify it, well, if you make your domain in certain way, for example, if you are saying that the flow is two-dimensional, then you can automatically ignore the Z terms, correct? Similarly, if your Reynolds number is really, really large, then what happens? Like this, what happens to these terms, right? You can make some approximations there. Similarly, if your pressure drop is very, very small, then you can ignore that. So, but these techniques are done only for analytical calculations. For flow simulations, if you're doing CFD, you should always solve the entire Navier-Stokes equations. If you're just ignoring some terms, your answers will be completely wrong. So like I said, computational testing is all about taking these equations and solving it using a CFD program. Now let me ask another question. This is mainly for people who have used at least one CFD tool so far. So if you've played with ANSYS Fluent, if you've played with ANSYS CFX, Converge, Star CCM, or any other software, CFD software, then you would have definitely seen more equations, right? There are more governing equations in CFD. Can anyone tell me what some other governing equations are? In addition to this, can anyone name a few other governing equations? Energy, Shahzad energy equation is already there. We have total energy, which basically conserves enthalpy. Euler's equation, well, that's actually wrong. Euler's equation is basically an approximation from the original Navier-Stokes equations, correct? So what Euler equation says is basically, if you assume inviscid flow, then you get the Euler equation, correct? So that is not right. Equation of state, sure, I can give that as a yes. All right. What about others? Entropy equation. So Dhruval, what do you mean by entropy equation? Are you talking about, yeah, I'm not sure what you mean by entropy equation. What other conservation equation? So especially Nitin, I'm assuming this is the same Nitin from yesterday's workshop. So you run a lot of CFD simulations, right? And you're using Converge. Is this all the governing equations that you solved, Nitin? Okay, Dhruval, yes, you are right. So with respect to CFD solvers, there are a lot of equations, and especially there is two equations that pretty much everyone remembers. And this question is primarily intended towards guys who have already done CFD simulations. You must have done this. I'll give a clue. There are two terms. The first term maybe is K. The second term is K dash epsilon. K epsilon equation or K omega. Sure, why not? What is this equation for, Shahzad? This equation is for turbulence, and we call K and epsilon as conservation equation, correct? So my question is, I basically said that your Navier-Stokes equation, right, or your continuity, momentum, and energy equation is sufficient when you're doing CFD simulation. Then why do we need additional equations for turbulence? Can anyone answer this question? When I initially started the call, I basically said you have these equations and 1, 2, 3, 4, 5 equations. If you solve them, you should be able to solve your fluid. Then why do we need two other equations for turbulent flows? Shahzad, shear stress has 6 unknown terms. Well, you need to understand the shear stress depends on the velocity, right? Tau depends upon velocity. So it's not 6 unknowns. So if you know x, y, z component of velocity, then you can determine your shear stress. We cannot consider all turbulence scales, so we model. Well, can you rephrase? But can you just explain it a little bit more? Why cannot we consider all turbulence scales? We can consider all the turbulence scales. For accurate understanding of turbulent flow, that's completely wrong. When you're using a turbulence model, you're approximating turbulence. Remember that. Akhilesh, turbulence causes disruption in the momentum equations. Not sure where you're going with it, but that's not correct. Turbulence is nothing but chaotic flow, but at each and every point, if you are basically calculating the velocity accurately, that means you're also keeping track of the turbulence fluctuation. So why aren't these equations enough? The closest answer is given by Nitin, but even that is not complete. The actual answer is exactly. You can actually do something called as a direct numerical simulation. The name sounds fancy, but it is basically solving the entire Navier-Stokes equation as is. If you do that, then there is no need to have any turbulence model, right? But the problem is the number of computational cells that you need is actually a function of Reynolds number to the power 9 by 4. So this, you can assume that this is roughly Reynolds number to the power 3. It's not accurate, but it does the math for us. So if your Reynolds number is 100, then you need 1 million cells to get all the scales, which is fine, which is something that you can do very easily. But if your Reynolds number is 100,000, right, it's pretty much impossible to do a direct numerical simulation. So in other words, you cannot capture turbulence by directly solving these equations. So what you're doing is you're trying to approximate it. And that is where the turbulence model comes into play. And we have something called as the law of the wall, which basically helps a turbulence model so that even with a larger cell, you can basically run turbulent flow simulations. And this is kind of an important point in CFD. Many students who run CFD simulations think that when you use a turbulence model, you're accurately capturing turbulence. Remember that you're using a turbulence model because you don't have any other way. Especially if you're running simulations for flow over an airfoil or flow over a truck or something like that, it is impossible to get that type of a resolution. Impossible. For the next 30 years at least, I don't think you will be able to do it. Anyway, moving ahead. So make sure that you understand Navier-Stokes equations, and only then you will be able to get into CFD and understand it properly. So we still haven't explained one thing. How do we take these partial differential equations and how do we solve it using a computer? Well, that is where the concept of numerical discretization comes into play. So let us say we take our x momentum equation, right? So in two-dimensional viewpoint, it's going to look something like this. Minus dou p by dou x plus mu times dou square u by dou x square plus dou square u by dou a square. So this is your governing equations. It's a partial differential equation. So in order for me to solve this in a computer, looks like there's a question. How we solve it conventionally without a computer? Well, Rushikesh, if the PD is simplified, right? If the PD is simplified, then you can solve it without a computer. You can solve it in pen and paper. The truth is, you cannot solve Navier-Stokes equation completely on a piece of paper. If you can do that, then you would have solved what is called as a millennium prize problem. So the Navier-Stokes equation, proving that the solution or a unique solution exists for Navier-Stokes equation is an unsolved problem. It has been unsolved for more than 100 years now. So if you're able to solve it, you will literally be given $1 million in cash for solving it. So till that is being solved, you need CFD. So conventionally, we can't solve whole Navier-Stokes equation. Exactly, that's what I'm talking about. So if you take partial differential equation, I need to convert this into a form that can be solved using a computer. Well, that is the concept of discretization. So a partial differential equation is continuous, meaning at any point in x, this equation is valid, and if I solve this equation correctly, I can actually get u as a function of x, y, z, t at any point, right? But with discretization, what you are doing is you can calculate u, but it can be calculated only in certain points. This certain points is what you call as a mesh. So you might have heard of people saying computational mesh, right? Well, that is basically a space or a domain in which this partial differential equation is being solved. So how does it work? Well, the concept is actually quite simple. For example, say that you have a function, right? So I have a function like this, f of x. So what is df by dx? If I know the analytical, for example, if f is x square, then what is df by dx? Maybe actually I'll draw that same function so that it'll be easier for me to explain. So for example, let us say we take the function y, something like y equal to x square. All right. So let us say we take x is equal to 1, right? So this is 0, this is 1, and this is 2, right? So at this point, what is the value? When x is equal to 1, y is equal to 1. But what is the value for dy by dx? When x is equal to 1? That's going to be 2, right? I hope you guys can see it. Exactly. So now what I'm going to do is, I'm going to approximate this derivative. What I'm going to say is, well, my domain is not continuous. I'm just going to have 2 points. So what I'm going to do is, I'm going to maybe change the color here. I'll take this point, and maybe I'll take a point somewhere here, right? X equal to 2. And then what I'll do is I'll compute the derivative based on these 2 points. So the first thing is, when you're doing this, the derivative that you're computing is this guy, correct? So that is what you call as the slope of the curve, correct? Whereas at x equal to 1, the slope is actually like this. This is the actual slope, and this is the approximated slope. Like, how do you do the approximation? Well, you can say that if I calculate y at 2 minus y at 1 divided by x at 2 minus x at 1. What is y of 2? When x is equal to 2, y is x squared, so that's going to be 4 minus 1 divided by 2. So that's going to be 3 by 2. That is going to be 1.5. So delta y by delta x is going to be 1.5, which is wrong, whereas the actual derivative is 2, right? So this right here is what you call as numerical derivative. And this right here is called as the analytical derivative. But this gives you a very big advantage. The analytical derivative is good, but numerical derivative gives you a big advantage. Meaning, see, if you have a function, right? If you have a function like this, well, you know that. See, if I know the function's value at a present location, right? At a particular value of x, if I know my function value, then what I can do is I can use this formula. Which means I can use f of x plus delta x is equal to f of x plus delta f by delta x into delta x. This right here is no longer a partial differential equation. And remember, here this f can be any function, right? F can be anything. And this right here is a simple approximation based upon, if you just wait for it, this is nothing but your Taylor series. F of x plus delta x is equal to f of x plus f dash of x delta x by 1 factorial plus f double dash of x delta x squared by 2 factorial and so on, correct? So this is the Taylor series, right? It's an infinite series. What you do, like after your second term, you just ignore everything. That is how the approximation of slope is considered. And this right here is what you call as the first order approximation. This, my friends, is the process of discretization. And since we are discretizing above a point using Taylor series, this discretization technique is called as the finite difference method. All right. So similarly, you have other techniques for discretization, which are called as finite volume method, and finally finite element method. So you need to understand all these three methods, like depending upon what type of computational code you have, and you need to discretize all of your equations. When you discretize all of your equations, you will basically end up with a linear system which you have to solve, which is basically a matrix. When you solve that matrix, you're getting your values for velocity, pressure, temperature, from which you can calculate shear stress, from which you can calculate your drag coefficient. Okay, so that is basically like basically a 101 of CFD. There's so many details I skipped, but I would be happy to answer any questions that you guys have. Does anyone have any questions? Was the explanation clear, or is there anything that needs to be explained again? Please let me know. Where do we use the other methods? Well, for computational fluid dynamics, the most commonly used method, does anyone know, especially the guys who do CFD? Which method is the most commonly used method for computational fluid dynamics? Shahzad, FVM, Rushikesh says FVM, Nitin says FVM. Why? Can anyone tell me why we use finite volume method? Like finite difference method is perfectly capable of doing the job. Why do we use finite volume method, Nitin? Or Shahzad? Locally conserved in cell. Why is this not conserved? Why is finite difference method not conserved, right? You're solving the full conservation equation, but why is it not conserved? Even FEM would also give you, you need to understand that you're applying this discretization principles to the original equation. So why would it not be conserved? So Bhavana, your question is correct. Why not finite element method? That's actually a very loaded question. The answer is not that simple. And the actual answer is you can pretty much use any method you want. But the reason why finite volume method is the most popular for CFD techniques is because nowadays with computational fluid dynamics, the type of geometry that you can handle is becoming very, very complex. For complex geometries, finite volume method is much more beneficial because in the derivation, you don't make any type of approximation about what is the shape of the cell. In finite difference, you assume that it's a point and you assume that your grid is Cartesian, meaning your computational grid looks like this. Whereas in finite volume method, you are basically discretizing what you call as an integral form of governing equation, which is derived for an entire volume. And the shape of the volume is not taken into account at all. So it can be used for any shape. Similarly, finite element method is based upon shape functions. It can absolutely be used for CFD. The reason why you don't use it for CFD is because at the end, when you're solving the linear system becomes much more larger than what you get with FEM methods. So it is not efficient. And that is why finite element method is typically used for structural simulations, whereas finite volume method is typically used for computational fluid dynamic simulations. Finite difference method can be used for all of it for simplified cases. So that is why when you try to learn CFD, people typically teach finite difference method because it helps you learn all the fundamental concepts in CFD. However, for complex geometries, you cannot use finite difference method. Okay, all right. So I know that I kind of went into a lot of technical details, which might have bored people who are still beginners. But for beginners, you need to understand that there's a concept of discretization, which is nothing but creating the mesh and solving the equations. When you discretize it, you can actually solve everything using a computer program. All right. So let me just finish that with a very simple example. So in my Navier-Stokes equation, what I can do is I can just ignore a lot of terms. And I can come up with a very simplified PD, dou u by dou x plus u times dou u by dou t plus u times dou u by dou x equal to 0, right? So this is called as the linear convection PDE. Why? Sorry, that's the nonlinear convection PDE, but I can write the same equation with a constant velocity c in front, and this equation is called as a linear convection PDE. Why? It's called one-dimensional because yes, we have cancelled out all the derivatives. It's called as the convection equation because we have dropped the pressure and diffusion terms, so only convection is remaining. So if I discretize this, this is quite simple. So this is u at u new minus u old divided by delta t. I'm just using my slope formula is equal to minus c times u old at x plus delta x minus u old at x minus at x divided by delta x. So the superscript is basically so the superscript is the time index and the subscript is the space index. So with this, what I can do is I can say u new at x plus delta x is equal to u x plus delta x, the old value, minus c times delta t by delta x multiplied by whatever we have here. This is a very simple update rule. This is called as time marching. I'm not explaining the details here because that is something that I don't want to do right now. Let me see if I have MATLAB. Oh, unfortunately, I don't have MATLAB in this computer, so I cannot show you a demo. That's fine. That is something that I can show later. So the basic idea is this right here is no longer a partial differential equation. This is actually an algebraic equation. And who is great at solving algebraic equations? Well, your computer is. So you take this equation, you feed it to your computer, it's going to solve it, right? And this is what you call as solving the linear system. And depending upon how you structure your equation, you can get a system of uncoupled simultaneous equation or a system of coupled simultaneous equation. This is what you call as explicit and implicit. And if you do that, your results are going to change, and you'll basically be able to solve the system, which means you'll be able to get the velocity profile. So this is just for linear convection. Similarly, if you have additional equations like momentum, like continuity equation, momentum equation, energy equation, you can follow a similar procedure. This procedure is what people call as a solution algorithm. And at the end of the day, you will always end up with a matrix that is called as a linear system. And to solve the matrix, there are several methods. These are called as linear solvers. And when you solve it, you get your answer. Okay. So moving on, well, how do you do all of this in a software program? Well, here I have a simple software which is called as Convert CFD, right? This is the company that I worked for, so I'm very comfortable with the software. So with Converge, you can do external flow simulations, internal flow simulations, pretty much anything that you want. So here what I have is I have an airfoil. So if you zoom in here, you can see that I have an airfoil. And what I'm doing is I'm simulating the flow over it. So the first step that I'm doing is I'm creating a box around my airfoil. This is what you call as a virtual wind tunnel. Why virtual? Because you're doing it in a computer. And through this particular phase, right, that I've selected, through this phase, you have your inlet air coming in. And you have an outlet on the other side through which air escapes out. And then on top of the bottom, you have symmetry boundaries. And then at the airfoil, you have a no slip boundary condition. So that's what boundary condition means. For each and every part that you have in your domain, you need to provide the boundary conditions, because at the end, you're solving partial differential equations, which require boundary conditions, correct? So when you do this, what you can do is you can use this information. Let me just go back to this particular layout, right? So the first thing that I do is I take my CAD geometry and I convert this into a form so that I can create my computational mesh. Then what I do is I basically set up, for example, what are my materials? And then I set up my simulation parameters, meaning how long should the simulation run, right? So in this case, I'm doing a steady state simulation. Why am I doing a steady state simulation? Well, when you're doing aerodynamic flow analysis, your end result is going to be a single value of drag coefficient, right? So that is why we do a steady state simulation, because you can get there faster. And then as far as simulation time parameters, this is where you provide, okay, how many iterations should I run for? In this case, I'm picking 20,000. That is based on experience. And then there are certain values like what are the time step size? Well, what is time step? Well, if you see in this equation, you have time step, and this right here is a computational mesh. So that is why it's very important to learn to code CFD, because when you're learning to code CFD, right, things like time step, things like CFL number, stability criterion, you will understand that very quickly because you're coding it on your own. If you're using an application package like ANSYS, if that is your first interaction with CFD, then you will not be able to learn these terms. That is the problem. So if I go back to the solver, you can see that there are so many parameters like time step, and there are 3 CFL numbers. CFL stands for your Courant numbers. They determine the stability of your system. So we are setting up particular values for those. And these constants are found in any software. Like it could be ANSYS Fluent or Star CCM, you will find the same constants. Maybe the names would be slightly different. And then, as I mentioned, we provide the boundary conditions. So here the boundary conditions are pretty easy. If you look at the airfoil, we basically say that it's a stationary wall, and we provide the law of the wall boundary condition. Looks like there is a comment. What is CFL number? Well, CFL stands for Courant. It's a Courant number. So F stands for, actually CFL, C stands for Courant, F stands for Froude, and L stands for Levi, right? So, but usually you call it as Courant number. This actually explains to you, or this actually says what is the stability of your numerical discretization. To put it in simple words, see, in the process of discretization, right, we are actually ignoring some terms, correct? For example, to compute the slope, we are ignoring the higher order terms. Because of this error, your solution of the system is going to be sensitive to the computational mesh size and also to the time step size. There is this number, magic number called the CFL number, which is, in this case, let me just show that here. C times delta T by delta X. This is called as the convection-based CFL number. Why? Because this is the convection equation. This number, if it's greater than 1, then your system becomes unstable. So when you're trying to solve it, your results will be completely garbage. It's going to be unphysical results. So if you see in converge, this CFL, look at that, that's maximum convection CFL. So that is what it is. It's mainly for your momentum equations. Similarly, on the diffusion side, you have a different CFL number, which basically says if your quantities are diffusing very fast, then your solution can blow up. So that is the CFL based diffusion number. Finally, you can have a CFL number based upon the compressibility effect, which is called as the max CFL number. It is based upon the speed of sound, right? So all these factors contribute to how stable your system is. Typically, setting it to a lower value means your system will be stable. If you increase these values, then your simulation will run fast, but you are basically running the risk of crashing your simulation. All right. So then, like I said, we assign boundary conditions and then we assign initial conditions. So these two concepts are something that you do for any partial differential equation or ordinary differential equation that you solve, correct? So you set that up, and then comes your turbulence model, right? So this is where there are so many models. Typically, if you're running external flow simulations, you need to be using K omega SST, and this is where, guys, people who are doing external flow simulations, when you're doing K omega SST, your Y plus value, there's a quantity called Y plus. Try to understand what it means. Your Y plus value should be less than 1. What does this mean? Well, your first cell should be at a boundary layer, which means your computational mesh size based upon your Reynolds number should be around 1e minus 5 if it's an external flow simulation. So if you're using that small of a computational mesh, your total cell count will be huge. So for external flow simulations, if your total cell count is less than 30 or 40 million, then the results are completely wrong. If you have 40 million cells, there is no way for you to run that on a desktop computer. So that is why Deepak and others, I basically mentioned that your simulation strategies are incorrect. I hope that makes sense now. So how do you fix it? Well, you can use a K omega model with automatic wall functions and maybe reduce the mesh count a little bit. But then if your Reynolds number is huge, even that mesh resolution that you need is going to be it's going to be very small. Okay, all right. So let me close this guy and close this guy. Then comes the grid. So this is the basic discretization along the X, Y, and Z directions. We provide that. And Converge uses a technique called adaptive mesh refinement, which is very cool. I'll explain that to you. And then we have fixed embedding, which is local refinement, which is fairly easy to understand. Looks like we have a few questions. What is Y plus value? Y plus is basically a non-dimensional wall distance, Deepak. It basically says it basically says, where are you with respect to your boundary layer? If your Y plus is less than 1, you are inside your boundary layer. You are in what you call as the viscous subregion, right? So if you have to understand Y plus correctly, try to understand the difference between laminar and turbulent boundary layers. You should be able to get it. Any way to predict Y plus before running simulation? Absolutely. So there are a lot of correlations. So there's a correlation to predict your Y plus value based upon flat plate boundary layer studies. So you use that. Usually you have a formula which basically says for a particular Reynolds number what the Y plus is. You can use that formula to predict a baseline value of Y plus and use that as your starting point. And then what you can do is you can just run the simulation and see what the Y plus you are getting, and then you can make adjustments accordingly. Usually it is very close. Does that make sense, Shazad? Cool. All right, so here we set that up, and then we are all ready to run the simulation. So the nice thing about this methodology is if you're able to get that for say one case, then what you can do is, let me just open up a case that you guys would find more interesting. All right, so there we go. So that has loaded, which is good. Okay, so this right here is a virtual wind tunnel. All right, the wind tunnel is kind of shaped weirdly because this is something that I set up in the last minute. So this is not a super accurate simulation, but this kind of gives you a lot of basics. So this right here is a virtual wind tunnel, and sitting inside that is I hope some of you can recognize this. Can anyone tell me what is this? What type of a vehicle this is? It's actually a FSAE car, right? It's not the F1 car, but this is an FSAE car. So, so this right here is a virtual wind tunnel setup. So if you're doing something like this, and if you really don't have time to learn CFD, what are some things you need to make sure that you don't miss? Well, the first thing is you need to position your vehicle correctly. This has been positioned incorrectly, meaning the upstream and downstream distances are really, really small. The upstream distance should be at least, that depends upon the experiments. The downstream distance should be at least 10 times the length of the car, which clearly in this case is not. But for demonstration purposes, this is fine. Similarly, from the top view, this thickness or this width is really small. Usually this should be at least 10 times the size of the width of the car, which clearly in this case is not. But as I mentioned, this is purely for demonstration point of view. But then all the software setup, the simulation setup is pretty much the same, right? So in this case, I ran the simulation and I ran it very coarse. And this is how the results are going to look like, right? So for example, this is the post-processed result. Maybe I'll use a black background so that you can see what's going on a little bit more clearly. Okay, so this is the FSA car. And note that I'm coloring everything by velocity, right? So for example, you can see that wherever the tire is present, there is low velocity region. So that typically means that's a high pressure region. And consequently, if I color this, say F1 car with pressure, that's going to take a little bit of time. And then what I can do is maybe color this guy with, or just change the labels. It's not the labels, but the legends. I'll change the color a little bit. There we go. So now the car is colored by pressure, all right. I'll just hide the other things so that it doesn't cause a lot of confusion. So the wing, for example, is colored by the pressure. And this is a classic picture that shows downforce. And if you see the bottom side of the wing, that is colored by pressure as well. So what you can learn from this particular image is the concept of downforce. You have higher pressure on top, and lower pressure. This means visually or qualitatively, this result makes sense. Similarly, what are the other high pressure zones? Like if you look at your front wing, see that there is high pressure on the top and low pressure in the bottom. So in your wing, you are generating some downforce. The front wing, you're generating some downforce. That makes sense. But in this case, since it's FSAE, the end plate configuration is not great, though there is some amount of deviation. So if I put this car in the front view, right? So you can see that there is some amount of, if I use the red color, there is some amount of deviation in this direction. It's not a lot, but there is a little bit of deviation. Ideally, if you try to kind of channel your airflow like this, then that can be very good for the aerodynamic performance. But again, would I trust this result? To be honest, not really. This was actually run with a lot of cells. So I think I ran it with around 0.5 million cells. But like I said, any results that you're getting that is less than 20 million cells, the answers are probably wrong, right? So let's actually take a look at the computational mesh. So for example, here we have the computational mesh, and the technique that I'm using here, if I just enable it here, is what you call as adaptive mesh refinement. So let's hide the stream tracer, maybe hide the plane. And if we put this in the front view, this is called as adaptive mesh refinement. What's happening is, let's say we hide the grid. So this is actually your velocity distribution in this cut plane. Now what's happening is, wherever there is large gradients in the solution, right? So which typically happens when flow encounters an obstacle, right? There's going to be large gradients. And to be very specific, it's actually not gradients, but it's actually curvature change. So that's what you call as second order derivatives in velocity or temperature that can trigger the adaptive mesh refinement. And the solver is automatically adding more cells in areas where it requires. So the nice thing is, you don't have to guess. You don't have to guess where the computational mesh should be refined. The solver is doing it automatically, which is much more consistent. Because if you're doing it manually, you will definitely not be able to predict how big the wake is. So in the same example, for example, if I rotate the model like this and change the plane like this, look at that. That looks pretty interesting, right? Your wake region is pretty big, and the solver is kind of automatically refining it. The problem is this refinement is still not enough. Your simulation results are still not going to be that accurate. But this gives you this is what you call as a baseline result. Meaning with the baseline results, you know that your simulation is running. So the only thing that you need to do is increase the computational mesh resolution. Okay, any questions on this particular operations that I'm doing? What I'm doing right now is called as post-processing, which is basically taking results from your CFD simulation and then analyzing it. Okay, so especially guys who are interested in doing this type of analysis as part of your FSAE or Supra programs, make sure that you gather adequate funds for getting the computer hardware. So personally, like for what we do is, in addition to running these type of simulations, we also do research work where the simulations are much more complex and we have specific computers. For example, we typically run external flow simulations on a machine that has 16 cores. We have another machine that has 24 cores, and they all have about around 190 gigs of RAM. So those are the machines that we use for research or really high quality simulations. For demonstration purposes, we use this machine which just has 16 GB RAM. Okay, but again, I hope you guys okay. There is a question: how will changing the rake of the car affect the aero? This simulation looks like the car has a 0 rake angle. Well, see, that depends upon the car, and obviously it's going to affect. So in this case, the yaw angle is set to 0, right? And that is, it depends, right? So for example, when F1 cars are tested, the aerodynamics simulations are done, and the hardware and all the settings that control the hardware are optimized for each and every race. Why is that? Well, for different racetrack, you need different types of performances, right? So in this particular case, since this is just a proof of concept, right? Meaning we really don't have any type of experimental data on this particular model. So the easiest thing that you can do that makes the most sense is to set the yaw angle to 0 and run the simulation on it. And that's what we are doing. Does it make sense? Okay, cool, great questions, guys. We are actually at 7:30, so I'm, that's exactly the time that I had planned. So I'm glad that we are on track. Any other questions? Does anyone else have any other questions? Okay, cool. All right, guys. So, I hope you all learned a little bit about aerodynamics and also about computational fluid dynamics. So the next time when you do CFD, hopefully you do it a bit more cautiously. And as far as this workshop is concerned, you will be given a certificate, and that certificate will be sent to you along with the recording of this presentation somewhere in the next 2 weeks. So make sure that you check your promotions folder and also your spam folder, because sometimes our emails end up there. How to fix the meshing type and its size? That's a great question. So as far as the size is concerned, Rishikesh, that is where the Y plus criterion needs to be followed for external flows. As far as the meshing type, that's very tricky. So usually, for example, the mesh that Converge uses, and if I just enable it and put it like this mesh is what you call as a cut cell Cartesian mesh. In terms of numerical discretization, or with respect to numerical discretization, cut cell Cartesian meshes have the highest quality. Meaning, with respect to interpolation or gradient computation, these meshes offer the lowest error, which is amazing. But the problem is these are not suited very well in terms of an efficiency point of view, because when you're trying to simulate, for example, if I zoom in close to the surface, right? When I try to basically try to simulate flow over this face, I need to ideally have mesh that is like this. This is what we call as the body fitted meshing. So the mesh should be like this. This is also called as boundary layer meshing in certain softwares. Typically for external flow simulations, it's good to have this type of meshes. Cut cell Cartesian is good. It's going to give you decent results. But if you have to be thorough, you need to use this type of a mesh. And this cell size depends upon your Y plus value, right? And then the number of layers. So for example, what people do in aerodynamic simulations is near the wall, the mesh is very refined. Near the wall, the mesh is refined. And as you move away from the wall, the mesh becomes bigger. And there is a particular expansion ratio, which is called as E. This expansion ratio is very important. You need to check that as well. Rishikesh, I hope that answers your question. Shazad, a difference between steady and transient analysis. So the idea behind steady state and transient is quite simple. So in both cases, you are actually having time steps. Even in steady state simulations, there are time steps. There are intermediary solutions. The thing is, the intermediary solutions are not being solved accurately. So since your final results are important, you try to take really large time steps and try to get to the end time as fast as possible. Whereas in transient simulations, you are carrying about each and every time step. An example would be IC engine simulation, right? Only if you're getting your intake stroke correctly, your compression stroke would be correct. Only if you're getting compression correct, power stroke would be correct. Whereas in airfoil, it's not like that. Your drag coefficient will start out wrong initially, but then as the flow converges, it will settle down to the right value, which is a steady value. Does that make sense, Shazad? Cool. Okay. Great questions. Okay, so like I said, guys, the workshop is officially done. I thank you all for taking the time to attend, and I hope you all learned something useful. If you have any feedback, please do let me know in the comment section so that we can improve these workshops for upcoming batches. And if you have an idea for any other workshop, please put it in the chat window, and we'll make sure that we'll try to conduct a workshop on that topic.